In order to understand what is the meaning of potential energy or potential, which happens to be potential energy per unit mass, or the potential energy function or the potential function, we need to realize that potential energy is defined for forces that are classified as conservative forces. So one of the classifications of the forces that occur in the universe can be conservative forces versus non-conservative forces. So conservative forces are the ones for which work done happens to be independent of the path taken, meaning from point A to point B, let us say there are multiple possible paths. So let us say this is path 1. So the work done while the particle traverses the path 1 is W1. Let us say this is path 2 and the work done over here is W2. This is path 3 and the work done over here is W3. So let us assume that the particle has traveled from point A to point B via three different paths in three different time instances or time intervals. So as long as the force is conservative, all the expressions of work done and their values are going to be the same. So W1 is equal to W2 is equal to W3. So work done is path independent. This also entails that if a particle starts from a point P, traverses a certain path and comes back to the point P, then in that case the net work done is equal to 0. So work done for a loop, closed loop, happens to be 0 as long as the force is conservative. So what are some examples of conservative forces? So the naturally occurring conservative forces are gravity, electrostatic force of attraction, or repulsion. So the electrostatic force between charges, and the spring force, which is one form of electrostatic force. All contact forces are electrostatic in nature. So these are the three that are naturally occurring. Otherwise also, we can artificially mathematically construct the expression of a force that happens to be conservative in nature. So if a random expression for a force is given, then how do we figure out whether the force is conservative or non-conservative? For that, we write down the curl of F. So the curl of F is written down like so. So this is I cap, J cap, K cap. So this happens to be the del operator, which is dou by dou x, which means partial derivative with respect to x. This is dou by dou y, and this is dou by dou z. And this is fx, fy, and fz. So basically this expression means this is equal to I cap into parentheses dou by dou y of fz minus dou by dou z of fy minus j cap. This is how we expand the determinant, dou by dou x of fz minus dou by dou z of fx. This is the meaning of the determinant. Determinant is a shorthand for writing this expression. Plus k cap dou by dou x of fy minus dou by dou y of fx. So this expression happens to be the curl of f. This is called as the curl of f. So this is an operator which operates upon f to give a new vector quantity called as the curl of f. So in order to figure out or find out whether the given expression of a force is representing a conservative force or not, we just find out the curl of f, and if the curl of f happens to be identically 0 or 0 for any value of x, y, z, so the entire expression happens to be 0, means this parenthesis, these all of them are identically 0. That is when the value of curl of f is identically 0, means definitively 0 for any value of x, y and z. So when that happens, this implies and is implied by, so this is an if and only if statement, IFF, that f happens to be a conservative force. Incidentally, this curl of f measures how much a force circulates. So this is something extra that I'm talking about. So the circulation of a force F is essentially integration of F dot dr around a closed loop basically. So if the curl is 0, that means integration of F dot dr around a closed loop is going to be 0, and for a conservative force this happens to be the work done. So work done along a closed loop is 0. This is what is implied by the curl of F being 0. So this is directly from vector calculus, the definition of curl of f, and when the curl of f is 0, that implies and is implied by the fact that the force F happens to be a conservative force. So whenever potential energy is defined, it is defined firstly for only conservative forces. So whenever potential energy is defined, the method of defining the potential energy is as follows. We define potential energy by defining the change in potential energy. So du is a small change in potential energy that happens to be negative of the work done dw by the conservative force. So this happens to be minus of f dot dr. So this happens to be negative of the work done. Alright, so if I integrate this expression, I get delta u, the finite change in potential energy, is equal to minus of w, the finite change in work, is equal to minus of integration of f dot dr from initial point ri bar to final point rs bar. So this is how the potential energy is defined to be. Now if we want to find out the expression for force F from the expression of potential energy, then we need to identify whether the potential energy expression is given as a function of r, the radius vector, or it is given as a function of x, y and z coordinates. So here, if the potential energy function is given as x, y and z coordinates, then we can write down minus dou u by dou x I cap minus dou u by dou y j cap minus dou u by dou z k cap. So this happens to be equal to the force F. Also, if the potential energy is given as a function of r, the magnitude of the position vector, then in that case we write down minus dou u by dou r cap, where r cap is a unit vector pointing in direction of the position vector or the radius vector. So this happens to be F. So both of these stem from a more general equation. This is called as the gradient function of the potential energy. So gradient function of u with a negative sign happens to be f. So if f is given and then we need to find out potential energy or change in potential energy from f, then we have to use this particular expression. This expression we need to use. And in case potential energy is given and we need to find out the force F, then in that case we have to use this particular expression. So this particular expression may mean this value if potential energy is given as a function of x, y and z coordinates, and it may mean this value if potential energy is given as a function of r. Also, it is important to note the fact that the potential energy function is a function with which we can add or subtract an arbitrary constant. Meaning, let us say this is the potential energy function. Let us say u is equal to mgh. So potential energy here is depending only upon the height. So let us say I could add an arbitrary constant plus k over here, and this arbitrary constant k does not matter or it does not affect our calculations, because in all calculations we are always going to use the change in potential energy and never do we use the actual value of potential. So basically this implies that delta u is equal to mg delta h irrespective of the value of k. So this is just an example. So we can always add an arbitrary constant to the potential energy expression, because in order to find out the force, whenever we differentiate the potential energy using this expression or using this expression, the derivative of the constant is anyway going to be 0. This implies that we are free to choose the potential gauge, means we are free to choose, this is the word, we are free to choose the potential gauge, means we are free to choose arbitrarily the value of potential energy equal to 0. In this particular case, we can choose anywhere to be the value of any height to be the value of potential energy equal to 0. So the 0 potential energy position is the position above which the potential energy will increase as far as gravitational field of Earth is concerned, uniform field G is concerned, and below which the value of potential energy will decrease. So we can always arbitrarily choose the value of 0 potential energy or potential energy's reference point. That can always be arbitrarily chosen. So let us look at an example now wherein we are given the potential energy expression and we would like to find out the expression for force. So let us say u has been given to be x cube y sine z, where x, y and z are the x coordinate, y coordinate and z coordinate of a given point in a given xyz system. So this is a rectangular system, x, y and z. So x, y and z are the 3 coordinates. So if we do find out minus du by dx, so this is the partial derivative. This is actually, it's supposed to be dou u by dou x. It's supposed to be called dou u by dou x, not exactly du by dx, because that implies the derivative. So minus dou u by dou x happens to be equal to 3x square y sine z. Also minus dou u by dou y happens to be equal to x cube sine z, with a minus sign, of course, both of them, because we are adding a minus sign towards the left. Okay, so minus dou u upon dou z. So what is the meaning of partial derivative? We hold the other variables constant. So that is what it means. Other variables are held constant. So here we get x cube y cos z. So naturally the force is going to be equal to minus dou u by dou x. We can check out the expression of force over here. Here, this expression we are going to use. So the force is going to be equal to minus dou u by dou x I cap. So this implies this is equal to minus 3x square y sin z I cap minus dou u by dou y j cap. So that is minus x cube sin z j cap and minus dou u by dou z k cap. So that is minus x cube y cos z k cap. Alright, if we have to study the potential energy function in terms of equilibrium, so then in that case we use the fact that for all kinds of equilibrium force happens to be equal to 0. So here we, as per our own convenience, use the expression minus du by dr r cap is equal to 0. So this happens to be the force. That implies minus du by dr is going to be 0. So let us understand the possibilities as to when can minus du by dr exactly be 0. So we would like to draw the graph of u versus r. So there are three possibilities for such a graph. I am drawing all three possibilities here. Alright, the first possibility is that the graph of u versus r is like this, like a valley. The second possibility is that it is like a peak, and the third possibility is that the graph is like this. Familiarity with the concept of maxima minima will make us understand that here du by dr is 0 in all the three cases. So we are talking about the extremum points. So in the first graph we are talking about the minima. In the second graph we are talking about the maxima. And in the third graph we are talking about the inflection point, also called as the saddle point. So this happens to be a minima. This happens to be a maxima. And this happens to be a saddle point or inflection point. So the rate of change of slope of tangent as far as u is concerned. So here the tangent is something like this, and the tangent is changing slope from negative to positive. So from negative it is first becoming 0, then it is changing slope and it is slowly becoming positive. So the rate of change of slope of tangent, it can be observed, is positive. So the double derivative of u represents the rate of change of slope of tangent. So here the double derivative d square u upon dr square, this is the double derivative of u with respect to r. Here this double derivative is going to be greater than 0. Here exactly opposite is going to happen. So the double derivative d square u upon dr square is going to be less than 0, because the tangent slope initially is positive. Initially the tangent is showing positive slope, and later it's becoming 0, and then again furthermore it is becoming negative. So the rate of change of slope of tangent, which is what the double derivative represents, happens to be negative in case of a maxima, This is also apparent from the calculus theory of finding minimas and maximas, or in general to find out the extremas. We put the derivative of y is equal to f of x with respect to x to be 0, then we get all the extremum points. In order to identify the minimas, we put double derivative of y with respect to x to be greater than 0. All those points happen to be minimas. And for the points wherein double derivative is less than 0, all those points happen to be maximas. So here there is no particular tendency of the double derivative. So it is neither positive nor negative. Here the double derivative in fact happens to be exactly 0. So d square u upon d r square here happens to be equal to 0. So this is something to be remembered and noted. So let us say we take an example of a bowl. So this is a hemispherical bowl, and let us say we are keeping a marble at the bottom of the bowl. So if we do displace this marble, let us say by some quantity x, then in that case there will be a restoring force applied on the marble. So that is what is the meaning of the marble lying in the potential energy curve minima. Let us say if this bowl were kept like this, then in that case the marble that is kept on top of the bowl, let us say if we displace the marble by x, then in that case a displacing force is going to be applied. So that is how we interpret the potential energy maxima to mean. So that's the reason why in the first case we call this kind of an equilibrium as a stable equilibrium. Wherein the particle is trying to return back to its original point if it is displaced slightly. The second kind of equilibrium is called as an unstable kind of equilibrium. Wherein the particle is trying to get displaced if it is slightly displaced from its equilibrium position. The third kind of equilibrium is called as a neutral equilibrium, wherein it is equivalent to keeping the marble on ground. Let us say if this is plain ground, and let us say we are putting the marble on top of the ground. Now if we do displace the marble slightly with x, then in that case the marble does not have any tendency to either go forward or to come back. There are no tendencies involved. So basically that is the reason why we call this kind of equilibrium as neutral equilibrium. So these are the three types of equilibrium or equilibria that are of importance as far as the potential energy function goes. So here we have conveniently interpreted the potential energy function to be minus du by dr r cap, so that we can easily analyze the types of equilibria. Now furthermore, in some situations what happens is only conservative forces act. So whenever, like if only conservative forces act, that is any non-conservative or dissipative force is not acting. So conservative forces have this property that they try to conserve the mechanical energy of the system. So let's see what happens if only conservative forces are acting. On a system. So if only conservative forces act, then we can use the work energy theorem to say that the work done by the conservative forces is going to be equal to the change in kinetic energy. So this simply is the work energy theorem. So this work now is of conservative forces. So we have seen over here that for conservative forces, the work done is also defined as, so here we have seen that the work done is also defined as the change in the potential energy of the system. So we can use that fact and say that the work done happens to be the change in potential energy. So this work done happens to be equal to delta U. Rather, it's the negative change in potential energy. Here also we have seen that it is the negative change in potential energy. See, du is equal to minus dw. So dw is going to be equal to minus du. The same thing has been mentioned over here, right over here. Okay, so this is in the definition of potential energy. So we are using the definition of potential energy over here. So we get minus du is equal to delta Ke of the system. So let us see what happens now. So this is minus of change in U. Change in any quantity is final quantity minus initial quantity. So this is minus UF minus UI. This is equal to delta Ke. So this is Kf minus Ki. So change in U is equal to negative change in U is equal to change in kinetic energy. If you rearrange this particular equation, we get Ki plus Ui is equal to Kf plus UF. So this is nothing but initial mechanical energy initial. So this happens to be equal to mechanical energy final for the system. So this implies that the initial mechanical energy is equal to the final mechanical energy as long as only conservative forces are acting. This is important. It is important that only conservative forces act on the system for the mechanical energy to be conserved. So this particular expression is called as the law of conservation of mechanical energy, which says that if only conservative forces are acting, mechanical energy of the system is conserved. If only conservative forces act, then the mechanical energy of the system of the system is conserved. So let us say conservative as well as dissipative forces act. Then we cannot use the law of conservation of mechanical energy alone. So here only the mechanical form of energy, which is kinetic energy plus potential energy. Only this part of energy remains conserved. So in case that conservative as well as dissipative forces act, then in that case we would have to use the law of conservation of total energy. So we cannot use the law of conservation of mechanical energy in case where non-conservative forces are also acting. So basically if all kinds of forces act, then I am writing down one expression that is very useful. So this is directly implied from the law of conservation of energy. This expression would say okay, so this expression would say that energy initial, so whatever energy initially is present with the system plus energy gained minus energy lost is equal to energy final. That's it. So for the system, this is a direct implication of the law of conservation of energy. So initial energy plus energy gained minus energy lost is equal to the final energy. It is obvious, logically it can be obviously stated that this happens to be true. Okay,